We're continuing with section 14.8, Lagrange multipliers to variables, example 3. Find the maximum volume of a cylindrical can to be made from 100 pi centimeter squared of metal. So what is the constraint here? Constraint is that 100 pi centimeter squared metal. So what we need to do is to set up g of x to be the surface area of the can, and then the volume of the cylinder is going to be the function that we're optimizing. So v of r and h equal to pi r squared h is the volume. A of r and h equal to 2 pi r squared plus 2 pi r h is going to be the constraint. Equal to 100 pi is going to be the constraint. First thing, find the gradient of v, set it equal to lambda times gradient of a. Gradient of v is 2 pi r h and pi r squared. Gradient of a is 4 pi r plus 2 pi h and 2 pi r for the y, for the second coordinate. Set the first one equal to lambda times the second one, and you get 3 equations. And you get 2 equations, and then add the equation of the constraint, and so you have 3 equations. So what is recommended again is to solve for lambda and in the 2 first equations, and then set them basically using those. Find an equation that does not include lambda. Something that you see is there may be extra solution. For example, in here you see r squared plus 2 is equal to 2 lambda r, and you get r equal to 0 as a solution in there. It's safe to assume that that's not going to happen, because you're optimizing, and one of the dimension equal to 0 is not going to it's not going to give you the optimized value, basically. So solving, first lambda is equal to r over 2. The other one is by replacing r over 2 in the other equation, you get 2rh equal to 2r squared plus rh, or h is equal to 2r. Use that in the third equation, and basically you get 2 pi r squared plus 8 pi plus 4 pi r squared is equal to 100 pi, and solve for r to get r equal to 5 square root of 6 divided by 3. Then replace twice that is going to be h, and by replacing that back in the in the volume function, you get the maximum volume. Another example, which point on the surface of x squared, y squared, and z squared equal to 1 are closest to the origin? So this question actually gives you the constraint. This is the surface that you're trying to find a point, and you want to find the distance formula and optimize it. And so this is g of x and y and z is equal to x squared, y squared, z squared. Again, something to notice is these are functions of 3 variables now. And that's equal to 1 is the constraint. And then f of x and y and z is the distance on that point from origin. So distance from the origin is square root of x squared plus y squared plus z squared, right? The taking derivative with square root is always difficult. So we learned even in when we were doing calculus of one variable that it's easier to optimize the function to power 2, and then that would give you what optimization of the function to the square root of that value is. So we're going to make sure that we optimize this function instead of the square root of it. So now a gradient of g is going to be equal to 2xy squared z squared and 2x squared y z squared and 2x squared y squared z, and gradient of f is equal to 2x, 2y, and 2z. Now set then that equal to lambda delta f equal to lambda delta gradient f equal to lambda gradient of g, and then you get 2x equal to 2 lambda xy squared z squared, 2y equal to 2 lambda x squared y z squared, 2z equal to 2 lambda x squared y squared, and z. And then here you can simplify things a little bit and basically get 1 is equal to lambda y squared z squared, 1 is equal to lambda x squared z squared, 1 is equal to lambda the last one is x squared y squared. Now let's simplify some and see what happens. Setting, basically you can either solve lambda and lambda and lambda, and then set each of the right side of the equations equal to the right side of the another equation and solve. For example, if I set these two equal to each other, I end up with x squared is equal to y squared. Set these two equal to each other, I get y squared equal to z squared. So it seems like x squared is equal to y squared equal to z squared. So that was the solution out of the first 3 equations. But that's not good enough. We need one more equation. What is that one more equation? An equation of the constraint. So I have 2 equations getting to solve the equations related to the gradient, and then I need this one. Z squared equal to 1. But if all of them are equal to each other, they all have to be equal to 1. And that is x is equal to plus minus 1, y is equal to plus minus 1, and z is equal to plus minus 1. And so the last step is to plug in and see which was the maximum, which was the minimum. back again to knowing that the value of x, y, z is going to be plus minus 1, plus minus 1, plus minus 1. Plug it into the function, which is x squared plus y squared plus z squared, and f of those is always, all of those points is always 3, and so the closest distance is square root of 3, which is attained at 8 points, plus minus 1, plus minus 1, and plus minus 1. There are 8 points, right? 2 times 2 times 2 makes it 8. Now I click at question 14.8. See what is the maximum product of 3 positive numbers whose sum is 12. So here the constraint is x plus y plus z equal to 12, and the function is x times y times z, and then when you set the gradient of f equal to lambda gradient of g, you end up with basically the equation gradient of f is what? yz, xz, and xy. Gradient of g is 1, 1, and 1. And then solving gives you yz equal to lambda, xz equal to lambda, and xy equal to lambda. And after simplification, you end up with x is equal to y equal to z. This has to be plugged into the constraint, because that was the third equation in here, x plus fourth equation, plus y plus z equal to 12. And so after that, you realize that x equal to y equal to z equal to 4. Multiply 4 3 times, and you end up with 64 for this question.